Okay, welcome back. So this will be week 2 of our equilibrium experiment. Let's just quickly run through what we're going to do in this week's experiment. Okay, so the whole goal of week 1 experiment was we constructed a calibration curve that allows us to relate an absorbance value to the concentration of this complex. Remember, Beer's law, absorbance is directly proportional to concentration, and we have an equation that relates the two. This is our calibration curve. Wonderful. Okay, so what are we going to do in week 2? Well, in week 2 it's going to be a little different than week 1. Week 1 we had a large excess of iron which drives this reaction to the right, and we assumed it went 100% to completion. What we are going to do in the second week of this experiment is we do not have a large excess of one of these two reactants, and what we want to do is ultimately determine the equilibrium concentration, the equilibrium constant of this reaction, our Kc. Okay, so how are we going to do it? Again, we're going to mix a series of solutions in volumetric flasks. We're going to measure the absorbance values of these solutions. From our calibration curve from week 1, for each of our solutions, we know an absorbance value, and we can use our equation, we can use our calibration curve to calculate the concentration of this product. Okay, this will be the equilibrium concentration of this product because we mix the solutions, we let them sit around for a while, we allow the reaction to come to equilibrium. So what we can figure out by measuring absorbance values of our various solutions, we can use our calibration curve to calculate equilibrium concentrations of this iron thiocyanate complex. Wonderful. Okay. How is that related to an equilibrium constant? Well, remember, if we know equilibrium concentrations of everything in this reaction, we could calculate the equilibrium constant. And what's that going to be? It will be the equilibrium concentration of products over reactants raised to their stoichiometric coefficients. All the coefficients are 1, so all these powers are 1. Okay, so we're trying to calculate an equilibrium constant for this reaction. We better know the equilibrium concentrations of all of our products and reactants. Okay, so how are we going to do this? That's a great question. Let me look at this. I don't know. Let's just talk about it. We don't even need numbers. Okay, for each of the flasks that you make, just like last week, we make a bunch of flasks, a bunch of standards and volumetric flasks. We should know the initial concentration of iron in here, and we should know the initial concentration of SCN minus in here because we made the standards. And we can calculate these initial concentrations just the same way we did last week, using M1 V1 equals M2 V2. So for all of our standards we make in week 2, we should know the initial concentration of iron and SCN minus. So in our ICE diagram, remember that row I is initial concentration, we will know the initial concentration of iron, we will know the initial concentration of SCN minus, and we know the initial concentration of our product. 0, we don't have any initially. Okay, we know the concentration of our reactants have to go down, and the product has to go up because we're starting only with reactants. Do we know how much they go down or up by? No, that's what we're trying to measure. But suffice it to say, if this goes down by X, this will go down by X, and this will go up by X, because they react in a 1 to 1 to 1 ratio. So, what's the equilibrium concentration of iron 3? It's our initial, we know that number, minus X. SCN minus, our initial, we know that number. What the check is represents a number. And what is the equilibrium concentration of the iron thiocyanate complex? X. Okay, so how do we use our equilibrium concentrations to figure out an equilibrium constant? Well, if we knew the value of K, we could solve for X. Or, if we knew what X was, we would know all of these equilibrium concentrations, and we could calculate K. Well, what does X represent in this ice diagram? X is the equilibrium concentration of our iron thiocyanate complex. How do we figure out the equilibrium concentration of the iron thiocyanate complex? That is what we get from our absorbance values and our calibration curve. Rewind like 4 minutes ago, and you'll see that. So for each of these standards, we're going to measure absorbance values. We will know what the equilibrium concentration of this complex is. That's what we get from absorbance values and our calibration curve. So for all of these flasks we make, we know the initial concentrations, and we know what X is. We know the equilibrium concentration of this complex. So we can calculate the equilibrium concentration of everything in this flask, and we can use these values to calculate K. All right, so how many times can we calculate K? Well, for each of the flasks that we have, at least each of them that have this complex, notice flask number 1, this is kind of grayed out. Flask 1 does not contain any thiocyanates, so it should not contain any complex. So don't calculate a K for flask 1. But for flask 2, 3, 4, and 5, you should be able to calculate an equilibrium constant. You should be able to come up with an average equilibrium constant, and you should be able to answer all of the questions. Okay, I hope that makes sense, but we'll see. Okay, talk to you soon.